This is lecture number 14, and if you remember, we started the chapter 6, and this is a continuation of chapter 6. We have started discussion about the cavities, its stability, stable, unstable, and we also studied the criterion to find the stability of the cavity. And if you remember, these are two parameters G1 and G1 we can suppose to calculate. Now, what is cavity actually? Cavity is simply, if you have a laser medium like this and you put two mirrors on both sides of this medium, one is partially polished and other one is fully polished, then you can say it's a cavity. And these kinds of arrangement, it vary from laser to laser. Cavity will be there, but the polishing of the mirrors and etc. Okay, so a resonator or a cavity with the two plane mirrors, okay, and parameter G1 and G2 is equal to unity or less than equal to 1 or greater than equal to 0, if you remember in the last lecture. So actually now we are going to study the common cavity configurations. Common cavity configurations. So what is here? If we have two plane mirrors and this is a lasing medium, okay, and if we apply the formula and we calculate the G1 and G2, it becomes equal to unity, that is equal to 1. Okay, so this arrangement is satisfying the condition of stability, but it's marginal. Like if you go a little up beyond 3, then it will be unstable. Okay, so the stability is marginal, so that is why the product actually is G1 G2 is equal to 1. So what exactly marginally stable means? First thing, if product of G1 and G2 is increased a little, then it will be beyond 1, maybe 1.01, 1.1 or etc. So the stability become the cavity become unstable. Marginally stable means first thing is that it's very close to unity. Okay, so it means it's very difficult to align. Little bit misalignment here, what you will get, it will increase. Okay, and it will be maybe, it could be like 1.1 or 1.2 or etc. Okay, so that is why mostly we don't use two plane mirrors in the cavity. Okay, under certain circumstances it can be, but it depends on the situation, but it's very rare. So this is now what we are studying, the common cavity configurations. The first configuration what we study when we use two plane mirrors. Okay, so two plane mirrors, marginally stable. Okay, it's difficult to align, a little bit misaligned, and it's beyond the criterion of the stability. So this is one of the reason it's rarely used. Now if we move to the second slide, if the cavity resonator consisting of two spherical mirrors, so this kind of arrangement is called confocal arrangement. So this kind of arrangement is called confocal arrangement because we are using two spherical mirrors like you can see here. This is ideal arrangement, okay? It's stable, satisfying the criteria, okay? And G parameters, I mean it satisfies the G parameter criteria, okay? So if we're using the spherical mirrors, it should have a certain radius, okay? So what will be? So the radius of both these mirrors we are using is exactly equal to the separation between the two mirrors. Like this one, a focal point is here, and for this one, focal point is here. Okay, and if we calculate the G1 and G2 is equal to 0, okay, it means it has a margin. It has a margin. If you misalign, still it will stay stable. So that is why it's stable, and it's not that much difficult to align, and even it is misaligned a bit, still it will work and it will be stable. Okay, so जो पिछली स्लाइड हमने क्या पढ़ा था, अगर हम दो प्लेन मिरर यूज करेंगे तो वो स्टेबल तो होगा लेकिन मार्जिनल, मतलब ये है कि वो बहुत जल्दी मिसअलाइन हो सकता है, ओके, इट लूज द स्टेबिलिटी. इसमें हम जो स्लाइड में क्या देख रहे हैं हम कि स्फेरिकल मिरर हम यूज कर सकते हैं. स्फेरिकल मिरर यूज कर रहे हैं, इसका नाम दिया गया है कन्फोकल अरेंजमेंट. तो दोनों जो स्फेरिकल मिरर्स हैं वो उनकी जो फोकल लेंथ है वो इक्वल है उनके सेपरेशन, दोनों की सेपरेशन पे. यानी एक मिरर जो है वो लाइट को फोकस करता है दूसरे मिरर पे, और G1 और G2 जो है वो 0 के इक्वल है. इट मीन इट्स स्टेबल. अगर थोड़ी सी मिसअलाइन भी हो जाती है तो इट विल बी स्टेबल. ओके, this is ideal diagram, okay, and if you see here how it is misaligned, okay, so it's misaligned here. The focal point, the focusing for this mirror is here and this one is here, but still it will work. Okay, it will work and you will see lasing. Only thing is that if it is misaligned more than that, maybe it may lose the stability. ठीक होगी बात. Some important points are here. The focal configuration yield the smallest average spot size of any stable resonator. Spot size के बारे में हम पहले पढ़ चुके हैं. The waist, okay. The same thing, I mean, it's linking these things. Spot size. The confocal configuration, what it yields? The smallest average spot size of any stable resonator with the beam waist we already know. So occurring at the center of the resonator, and largest spot size occurring at each mirror. Okay. So what it defines? This defines the diameter of the output beam if collimated by a lens at that point. Here, waist, beam waist. Okay, this is the point where you can find out the beam waist, and this is the point where they have largest spot, and here this is the beam waist. Okay, so यही चीज इधर एक्सप्लेन की गई है. Smallest average spot size of any stable resonator with the beam waist is here, okay, occurring at the center of the resonator, and the largest spot size W1 is equal to this L lambda over pi occurring at each mirror. Okay. So what it defined is define the diameter of the output beam if collimated by a lens at that point. Okay. If you let one of the side will be partially polished and the laser beam will come out, okay. If the laser beam will come out, you have to put the lens and then you collimate it, or you focus to another point, okay. So that will also define the output beam if it is collimated. If you collimate it between the two mirrors, that will be the output beam diameter. Okay, at certain point definitely. On this slide, another configuration we are going to study, and it's called concentric confocal resonator. Previous was confocal and now concentric confocal resonator. What exactly happened here? You can see two mirrors. So both the mirrors focus the light at the center of the lasing medium, at their center. Okay, center of the separation between the two mirrors, L by 2. So what is L? L is the length, the separation between the two mirrors. So L by 2, it means half. Okay, so this is a radius of curvature is reduced is the lowest limit. Lowest limit. Okay. In the other case, the situation will be devastating if you reduce more, reduce here, and if it is focusing here, okay, and then expand again, and this one will focus here, then expand again, and that will not satisfy the condition. Okay. So this cavity is stable unless the radius of the curvature of the mirror is even slightly under L by 2. Slightly under L by 2. But if it moves more, let's suppose if it is focus here and this one is focus here, then it will become unstable. So it's much better to have a little less than L by 2. Okay, so if you increase L by, if you like, it has to be less than much better or equal, but greater than this one, that would be, I mean, like, you cannot make it stable. So because it focuses here, so that is why the alignment is not that much easy, okay, as compared to the confocal one. It's a concentric confocal resonator is difficult to align. Okay, so focus of each mirror is coincident and has difficult to align. Definitely, how can you make it like this? You need certain special technique for this one. Okay, even though it's stable, but alignment is a big issue here. Okay, now we move to the next configuration. What do you see here? This is called spherical plane resonator. Plane mirror, spherical mirror. Okay, and the focal point of this spherical mirror is exactly on the plane mirror. Okay, so it's a long radius of curvature of this spherical mirror. So here what you see, It's much better if it focuses on the other side, like on the plane mirror, and it can be a little bit more. It can focus here as well. Okay, slightly longer than the cavity. And this is not a bad arrangement in some certain kind of lasers. And it's very popular in low and medium power lasers. Okay, helium neon, argon laser. So what do they do? When they manufacture, one side they keep it plain and other side they make like curved. Okay, and it focuses here. So helium neon and argon laser, medium power laser, low power lasers, we use this kind of arrangement. Okay, it is possible you can have a different arrangement, but this one is easier because it's not misaligned easily. Okay, so mostly popular in gas lasers. Okay, and OC, optical coupler, optocoupler, from where we take the output. Okay, this plane mirror is fully polished. Okay, this one is partially polished. So output is coming from this side. So as I mentioned, this configuration can be used, and it's popular in some certain kind of lasers like a helium neon laser, argon ion laser, and this kind of lasers. Uh, but usually for a solid state laser we don't use this kind of gases. In a gases we can, but not in a solid state laser. Usually in case of solid state laser, whether we use concentric, confocal or confocal, we need tight focusing there in the medium. Okay, so what is written here? It is used in many commercial gas lasers. Okay, OC is spherical and HR plane allow the use of various configurations. Okay, here in place of plane mirror we can also use a grating. We can also use a prism here in between to tune. Okay, and etalon. So if you want to tune, and if you want to uh, choose a wavelength, decide a wavelength and a frequency, then you have to use this arrangement with the plane mirror. Eh, don't do the like if you use spherical and use a prism here, that would be a big problem in alignment and other things. So that is why in case of if you want to use a prism or a grating, then it's much better to use a plane mirrors on one side of the cavity. So I hope you understand this concept. यहाँ पे मैं क्या एक्सप्लेन करना चाह रहा हूँ कि एक साइड जो है प्लेन है, दूसरी साइड जो है वो कर्व है. ठीक है, और स्फेरिकल, तो स्फेरिकल प्लेन रेजोनेटर कहते हैं. और जो रेडियस ऑफ कर्वेचर है, जो रेडियस है स्फेरिकल मिरर्स का, इट्स फोकसिंग ऑन द अदर प्लेन मिरर्स. ठीक है, ये इस तरह की अरेंजमेंट गैस लेज़र में काफ़ी पॉपुलर है, लाइक हीलियम नियॉन और आर्गन लेज़र में. एंड द थिंग इज़ दैट कि इसमें जो आउटपुट है आपकी वो कर्व साइड से आती है और जो प्लेन मिरर पॉलिश्ड होता है. तो इफ़ वी वांट टू हैव अरेंजमेंट, अगर हमने वेवलेंथ डिसाइड करनी है या चूज़ करनी है, फ्रीक्वेंसी चूज़ करनी है, तो उसमें इस किस्म की अरेंजमेंट में हम प्रिज्म इंसर्ट करते हैं, ग्रेटिंग यूज़ कर सकते हैं. ठीक है, तो अगर हमने प्रिज्म कैविटी में इंट्रोड्यूस कराना है, देन you cannot, I mean, like both side you cannot use spherical mirror. That would be बहुत मुश्किल होगा उसकी अलाइनमेंट करना. Now in this slide what you see, this is a combination of two different kind of mirrors. One is concave and other one is convex. So it's called concave convex resonator. Concave convex resonator. ठीक है. Now this arrangement is not that much common, but still you can find. Definitely it is stable under certain conditions if we satisfy the G parameter equation. Okay, so like here, this arrangement is stable within the confined set out by the G parameter equations. Okay, concave convex resonator can utilize much more of the lasing volume. Okay, so what does it mean? ये आपका लेजिंग मीडियम है, ठीक है. तो इसमें से जब गुजर रही है लाइट, so when the light is passing through, it covers the maximum area of the lasing medium. So if it covers the maximum area of lasing medium, then it means what? Utilizing much more lasing volume. ठीक है. अगर if you have another kind of cavity here and you are using like this, it focus here or here or here or here, so it's not utilizing all the volume available here. But in this one, this kind of arrangement, all the volume is utilized. Okay, and what else here? Can utilize much more of the lasing volume, and if you take it out, it will focus outside of the cavity. Okay, this kind of arrangement is very sensitive to and misalign easily. Okay, what it's covering the whole mirror here. If you little tilt it, it will, like, light will pass through like this. Okay, so if this is your raising medium and you, like, this one is like this, a little tilt. Okay, so what will here? It will pass like this, misaligned completely. And this type of arrangement is very rare to use, even though it satisfies the G parameter, but it's rare due to certain reason. But when the gain of the medium is very less, then we can consider this kind of configuration to utilize the maximum volume. But to align is a hell of job then. Here you can see the example. This is spherical plane resonator. Okay, as I mentioned, that helium neon laser. Okay, this is your HR portion, this is OC portion. Okay, what I mentioned in the last slide, to take the output from the OC side. Okay, to take the output from the OC, you can also consider it, but if you take it output from here, the light will be expanding a lot. Okay, you have to collimate or etc. Here OC is a plane mirror, so you're taking out the light through this plane mirror. Okay, this is a helium neon tube, commercially available. So commercially available, this is concave, this is plane. Okay, and here what it's showing, that alignment on a helium neon tube. We don't need to touch this one, we only need to touch this one. In case of if you have both sides the spherical mirrors, then you may need to align a bit. But here you don't need to touch this one, you only need this one, like here, to align a bit, and you can get a lasing. Okay, so this The purpose of showing these diagrams so you can have idea how these cavity configurations are used, and especially in the gas laser and the plane and concave combination. So this is what it is shown here. The last slide of today's lecture, what it shows. There are two unstable resonator configurations. Okay. We don't need only stable resonators. Sometime in some certain kind of lasers, in some certain situation, we may need unstable resonator configuration. Okay. Especially if you are aiming to design very high power laser. Okay, excimer laser, carbon dioxide, TEA type, transversely. Okay. So this kind of lasers, I mean, if you have a stable cavity, it may damage, blast may happen. So that is why you may need unstable resonator here. Okay, like number of times light passes through, and after a while it automatically misaligned and light will go off. To avoid the blast till we are getting the laser. There are two figures you can see in the book as well. Figure 1, figure 2, sorry, AB. They are given the name AB. So part A, what it's saying here, a positive branch confocal resonator. Positive branch confocal resonator. Okay. So what it consists, first see, small convex and large concave mirror. Small convex and large concave mirror. Okay. This is concave mirror. Okay. This is convex mirror. This is big size, this is small size. So ultimately light will go off after certain passes, like here. The beam exits around the edges of the smaller mirror and has an annular shape, like here. Annular shape, maybe it's hollow from the center. Okay. Part B, this one, what it has, it's using two concave mirrors. Okay. A negative branch confocal resonators. So the beam is also annular in shape. So what exactly what exactly is happening here? This is the concave, this is the convex. Okay, so it does not focus here, maybe it will focus outside. Okay, so after a while, because the size of this one is smaller, so the light will go off. And what is happening here, this is a concave mirror, this is also concave mirror. Okay, size of this one is smaller, so the light will come here, it may focus here somewhere. After number of passes, the light may go out because the size of this one is smaller. Okay, so this kind of cavity we may need if we are using a very high power gain medium, very high. You cannot say a gain medium, the power, I mean very high power laser. So the laser that the gain medium having high gain, like carbon dioxide, excimer. Okay, in this kind of, you can use this kind of arrangement. How about if you use full cavity mirror, full size here, then it will definitely it will may blast, even though one is partially polished, because it's too much gain there. So that is why this is one of the example is given, that is unstable configuration. Few more points I have written here, or you can also see from the book. So these resonators are not stable. Light is not trapped in the cavity for a long, okay? At least for many round trips. It's not trapped. After few minutes or something like this, it will go out. After few turns, you can say, okay, or after few rounds, you can say, it will go out. So this arrangement is suitable only for user with high gain laser, as I mentioned, high gain laser. If the gain is already low, then it's useless to use this kind of, okay. Now another point, the primary benefit of an unstable resonator is allowing the use of total reflectors, okay, that would not be damaged by high power in the tens of kilowatts level. So the primary benefit, as I mentioned, of an unstable resonator allowing to use a total reflectors. You are not using here partially reflectors. Both are totally reflectors. Okay. Only thing is that after few turns, after few rounds, the laser come out because of that size difference in the sizes. If this kind of arrangement, I mean, if you make a stable like same size mirrors, then the cavity will definitely damage by sure. So gain is high, okay, so tens of kilowatts you can achieve even having this kind of unstable cavity. So what is mentioned here now, the output beam does not pass through the outer coupler, as you can see itself, as it does in a stable resonator configuration here. Okay. So an unstable resonator utilizes a large volume of lasing medium, like here. Here also somehow allowing efficient extraction of energy. So what exactly problem here with this cavity? Now you can see the problem with this configuration. The shape of the beam is not Gaussian. It's not a round shape which we need. Okay. This is one of the problem. Okay. If you want to make a laser where there is no problem with the beam shape, like in case of military laser, defense purpose laser, okay, you are not looking at perfect beam shape or something like this, then maybe you can use this one. But in scientific research, for research purpose or for a medical purpose, the beam shape is very important. So then you may not need to use this kind of configuration. Cannot be focused to a sharp point, this kind of beam. Okay, not sharp focused. You can focus but not sharp. Okay, it can be focused to almost as sharp as point when operating in a higher order modes. The modes are important here. Okay, higher order modes. Higher order modes. Okay, if you are operating in a higher order modes, it can be focused, but in the normal case it's not. It is focused but not that much sharp. So it's suitable for what? Material processing application, where the beam shape is not that much important. Okay, so this is what I wanted to discuss in this lecture, कि हमें सिर्फ स्टेबल नहीं, अनस्टेबल रेजोनेटर की भी ज़रूरत होती है, हाई पावर लेज़र में यूज़ होते हैं, लेकिन ये अनस्टेबल इन द सेंस कि आप दोनों तरफ जो मिरर यूज़ कर रहे हैं वो डिफरेंट साइज़ के यूज़ कर रहे हैं. तो आफ्टर कुछ टर्न्स के बाद जो है, कुछ राउंड्स के बाद लेज़र बीम आउटपुट पे चली जाती है, और बीम का शेप एक्चुअली वो नहीं होता जो हमें चाहिए, लेकिन ये शेप हम इस्तेमाल कर सकते हैं जहाँ पे बीम शेप इज़ नॉट वेरी इंपॉर्टेंट टू कंसीडर। जैसे मैंने बताया मिलिट्री डिफेंस एप्लीकेशन या material processing, you want to make a hole or you want to remove the corrosion or something like this, in this case is okay. But still we need unstable resonator as well. Thank you very much.